Right, so I'm recording from this point forward. Okay, and then hopefully right, there we go. Great. You don't have to try and remember it in that like register transfer language as long as you can state each step. I write it in register transfer language just to keep it short, but I'll write both answers out anyway. Okay, another minute. An integer? What are you talking about, man? Right, okay, let's go through. Okay, what's the first step? Where does it all start? Starts with a PC. What do we do with it? Other than chuck it in the bin. Right. Move it to the MAR. So that's a transfer. Who does the moving? Who initiates it? Well done. There is one person with a bit of sense. Control unit. The control unit, the brain of the computer. Okay. The control unit is responsible for the fetch execute cycle. Okay, so that was step one. What next? Not MAR to MDR. No, the memory pointed to by the memory address register is read and it arrives at the MDR. So we write that in little short form. Don't assume the examiner is going to know what that means, but you're saying you're reading. You're reading from that location and it arrives. So we do a fetch. Fetch the data at the address in, and I've still got residual water in my lungs there, in the memory address register. Okay, so that's our first part of our fetch. That's the start of the fetch. Okay, what's the next step? Yeah, we assume we've got an instruction. So we say, okay, whatever we've just got, dump it in the current instruction register. Assume it's an instruction. Might be a bit of data if we've gone wrong. Oh dear, I do apologise. Okay, next step. Once we got it in the current instruction register, right, good. We have remembered something. Decode. And what else can we do when we decode? What's the other job we can do? Yeah, we know how far it's going to be to the next instruction. So we increment the PC. So that's 5 steps. So that is the end of the fetch and decode. The rest of it, when we get into specific instructions, there may be more fetches that we need to do. Okay, depending on what type of instruction we've got and where the data for the instruction is. But in terms of what we are generalizing, that is the first 5 steps. What's the next step? There's only 2 more. Yeah, execute. So assuming we've prepared and we've got all the instruction data, we can get on and carry it out. Either carried out by the control unit or the arithmetic and logic unit, depending on the type of instruction. Okay. And the final step. So we've finished executing this instruction. What do we do before we get going again? Yeah, check for our interrupts. Good, good. And that is it. In essence, that is all a CPU ever does. They're slightly more complicated than that, but if you're looking at it in a very abstract way, that is all it's doing. Okay. Moving on. Next task. 3 components that make up a CPU. So these are not registers. These are the blocks, the logic things. So write them down. Oh, dear me. That's odd. Okay, that shouldn't take you very long. Right, what have we got? What's the obvious ones? ALU. What else? Oh, whoa. Just for those at home, the PC is not a component. Right, ALU is one. Control unit. Now, you may be scratching your heads to wonder what the third one is. It is memory. Now, I'm introducing that one because I've seen questions where they say state 3 components of the CPU and they classify memory, okay, as a component, even though it's like outside of the CPU. So you could argue that maybe cache is part of the CPU, but it isn't really. But just be wary of that in future. Okay. Next task, state all the registers. Doesn't like your drawing this now. I wish you could hide them. I'm going to give you some alternative names for a couple as well because sometimes they use them. Just the acronyms will do for now. Remember, a register is anything that stores a piece of information on the CPU. There are loads more than this, but these are just the abstract ones we look at. Okay, give me a register. Memory address register. Correct. Another one. PC. I always start with the PC because that's the start of the fair check cycle. MDR. CIR. Accumulator, which we always write as ACC. Status register. Okay, right. Two of these registers have got alternative names. The program counter is also known as the sequence control register. So that's sequence. PCs are better. It's shorter. Sequence control register. I hope the sound's a bit better on this recording because it was terrible for Mondays. It was aliasing like mad. Right, the MDR. It's also got another name, which is very similar. The MBR, memory buffer register, because it does act like a buffer. So that one's actually quite a nice. So that's memory buffer register. Right, okay. Oh, always doing that. Right, status register. Remember, this keeps track of the status of things in and within the CPU environment. Okay, it has got 4 flags. What are the letters and the purpose of the 4 flags? Write them down. I don't know whether they're going to specifically ask you in the exam about the flags, but they're important to understand. They're all single letters, if that helps. Okay, give me a flag. C. What's the C flag? Carry. Did we have a carry? Another one. V. Overflow. Remember, overflow can only occur when we do an arithmetic operation. Just not being able to fit a value in a set of bits is not overflow. Another one. N. What was that one? Negative. Yeah. The result of something we did was negative. We took 2 numbers away. One was bigger than the other, and it resulted in a negative. And there's one more. Remove yourself from that's an instant B2, that is. We don't say Z. It does it never sounds better. Like it never sounds it's like saying a trumpet underwater sounds better. You'd find it hard to blow a trumpet underwater, I tell you. The actual, the surface tension of the water and trying to push through that. It depends how deep you were as well. The deeper you are, obviously, there's higher pressure and your force would be. I don't think you could do it. It'd be a good experiment if you're up for doing it, though. Right, what is the correct way of saying that symbol? Z. Like the person. And that is for a 0 result. Right, remember the flags in the status register, they're there for when we want to do comparisons. Okay? Or we want to know what happened when we did something. It's the sort of thing that you don't worry about when you're working in high-level languages like C#, Python, C, and all that sort of stuff. You don't think about this stuff. But we're now having to think about this low-level code. Okay? There's something pure about writing programs in assembly language and machine code. You need to get to know the CPU that you're working with. It's not just some random device that you're using. You're actually intimately entwined with the way that the hardware works. Okay, so that is our registers. So let's get rid of that. That's good. You all sort of remembered everything. Right, so if we go back to the A-Level Computer Science OneNote, if you go to the software development section, which is odd, I don't know why this isn't with the hardware, but it isn't. There is, to start us on this journey with assembly language and low-level code, we're going to look at a system called Little Man Computer, okay, which was developed absolutely years ago. It's an abstract computer. There is a link to an emulator. There is a bigger emulator that does ARM style CPUs, but we're going to look at this one first. Just click on that link. If you can't open the OneNote, just search for Little Man Computer and it'll bring this up. So what we've got here is an abstract model of a CPU. And this one is very abstract. It's got, you can we'll just look around what we've got here. We have got an output area that can output numbers and characters. We have got over on the right hand side a block of memory. It's RAM, so we can read and write to it. Open the software development section, Oliver, 1.2. When it eventually opens. There you go. Let me try and zoom that in a little bit so it's a bit bigger. Yeah, that'll do. Right, so we've got this memory. We can see it's read-write because it's RAM. Okay, and what we can do is we can actually, and you can do this for real on a computer, we can actually put machine code instructions directly into memory if we wanted to. Okay, there are 100 locations numbered 0 to 99. That's because it is using 2 digits to represent the memory addresses. It can't represent any more memory. It's just the way they designed this. Each memory location has got 3 digits. Those digits are in denary. Okay, so the smallest value you can have is 0, and the highest value you can have is 999. The CPU is really simplified. It's got a program counter, which is currently at 0. It's got an instruction register, current instruction register. It's got an address register, which is a memory address register, and it's got an accumulator. Okay, so it hasn't got an MDR. It hasn't got a status register. One of the things that this has got, it can do decisions, but it doesn't formally have any way of showing you the result. Okay, which is a bit awkward. At the bottom, we've got an input box. This is the bit that will catch you out, and there's a robot blatantly stolen from the Android robot, or the Android robot was blatantly stolen from this. I don't know which way around it is. And it's got a speech bubble. The speech bubble gives you information. Okay, so when we're doing input, it'll put up there, it'll say, oh, and type something in or something or other. Okay, so this is the machine, the abstract CPU that we're going to try and work with. The left-hand side has got 2 big windows where it says assembly language code. In the left-hand window, if you just click in it, what it'll give you is a box, and that's where we can type some code. Okay, so we can type an instruction like that. Doesn't do much, but once we submit, what it will do, it will convert it into machine code. So we're going to write assembly language and it'll convert it into machine code. So if you just type LDA1, we'll go through the instructions in a minute, and then just click submit. If you screw it up, Okay, and you put like loader, or no, let's put Yoda. Did I put that? I'm going to put Yoda 1. And this is what throws you. You think, oh, what has it done? It hasn't done anything. No, if you look at the speech bubble, it says unknown instruction. Okay, and this, what we're doing two things at once here. We're looking at low-level languages. We're looking at machine code, and this is turning into Spanish Inquisition again. There's three different things going on here. We're looking at machine code, we're looking at low-level languages, and we're looking at assembly language. And then there is a fourth thing that we're looking at, which is how we translate from assembly language to machine code. So we are writing assembler. We are then getting that turned into machine code by our translator, which is called an assembler. Okay. The benefit of doing this, let me correct my error and put LDA. The benefit of doing this is that an assembler can spot errors in our code. So if we've used a mnemonic that doesn't exist, it can go, oh, you've made an error there. You've tried to do something that doesn't exist. Okay, but let's just have a look at what we've got here. So in the right-hand box, we have got our machine code that's been translated for us. If you look at memory location 0, you can see the actual machine code instruction. It is 501. Now, what did we say about a machine code instruction? It had two parts. What were the two parts called? Go for it. Yeah, yeah. Opcode and operand. This models this the same way. So 5 is the opcode for load a value to the accumulator. 01 is the operand. This is why we can only address 100 memory locations, because the operand can only be 2 digits. So you can have 0 to 99. Okay. Now what I could do is I could write directly into there. I can actually type 505 if I want to, and I've put an instruction at that location. So I can write in machine code if I want. But obviously, in order to do that, we need to know what the instruction opcodes are. Okay, let's just flip back to OneNote and that main Little Man Computer page where the link was. I've put here all the instructions. Confusingly, they have got more than one instruction for the same actions. Store and stat are both store a value. We've got imp or out, which are both instruction 9, but they use the operand to say whether it's input or output, and you do get a little bit of that when you're programming as well. You'll notice that there's actually an instruction that doesn't exist. There's a 4 there, and so that doesn't do anything. It's like an illegal instruction. And hardware manufacturers of CPUs will do this, and they will pick certain ranges of opcodes that are deemed illegal, and the control unit can like make use of that. Okay, and you can cause other things to happen. But these are the only instructions we've got. So let's just quickly have a look at these, and then we'll start writing some programs, and we'll do some running and stuff. Right, we've got a halt instruction. Stops. Little Man Computer hasn't got any interrupt, so that's the end of game if you do a halt instruction. So what we tend to do when we write our programs is we put a halt as our last instruction. This is decomposition on a massive scale. You've got to break things down into simplistic actions. Right, we've got an add instruction, which you could probably have guessed added. Okay, whatever's in the accumulator, we can add the value of a memory location. Little Man Computer only has variables, and I'll explain the consequence of that. It's a real pain in the neck. We've got a subtraction operation. Obviously, that subtracts. And then we've got store. Store takes what's in the accumulator, writes it back to memory. So that's our write operation. We've got load, which we've just seen, and I used in my example on Monday. Then we've got 3 branch instructions. The branch instructions allow us to do programs that are not linear. So we can make decisions. Branch. That's what we call it, branching. We have got three. The first one is called BRA. It's what we call an unconditional branch. It always happens. All branch instructions do are set the value of the PC. Okay, that's how you do a branch. You just change the PC so it's not a sequence. The other two are what we call conditional branches. We've got a branch if we got a 0 result. It's all right, I'm just coughing. That's my previous drowning. Right, and then we've got branch if the result is positive or 0. Okay, so 0 is classified as positive. You know this from 2's complement. Then we've got the input or output instruction. And the only thing that changes between those two, if we was to write it as a machine code one, is we put a 1 if we're to do some input and a 2 as the operand if we want to do output. But we're not going to rewrite it in machine code, so we just put imp or out. Okay. And then the assembler translates it for us. There is another version of out, OTC. What this allows us to do is output an ASCII character. So if we put 65, and we'll do this instruction first, if we put 65 in, we can output that as a capital A. And then the final one isn't an instruction. Okay, it's a directive. It's an instruction to the assembler. It says, this isn't an instruction, this is marking a piece of data. Okay, but we'll come on to that as well. Yeah, Hugh's just asked, good question. Unfortunately, the answer to that question, Hugh, is yes. You have got to remember them. Then, right, but come on, to be honest, is there anything there that you couldn't have half guessed? You might have thought BRP was burp. You might have done. I don't know what you'd have thought bra and buzz were, but yeah. Yeah, I mean, most of them are rememberable. Okay, and I will, over time, test you on these. Right, okay, so for now, we've got the ability to flick back and look things up. So let's go back to Little Man Computer then. Let's write a little program. Right, so what I'm going to do, I'm going to do the most basic program I can write. So delete whatever's in your assembly language box. And we are going to write a program that is going to load a value to the accumulator and output it as a character. Then it's going to stop. Okay, so I'm going to say LDA. Now this is going to be starting at memory address 0. And again, another thing that you don't worry about when you're programming, you don't worry about where in memory everything's got to be. But when you're doing this sort of code, you do have to worry about it. Right, we're going to load a value. We've got to work out what address the data is going to come from. I'm going to output this code. So I'm just going to put a marker. I'm just going to put 1. I don't know if that's the right number yet. I'll work it out in a minute. So I'm going to say LDA 1. And then my cursor's gone. Hang on. I'm going to... Oh, what's happened to my... Something's gone wrong. Hang on. Let me just reset. Why doesn't it go down to the next line? That's appalling. I'm assuming that's... Why isn't it flashing? Is it half in the box or something? No, I don't know. Right. That 1 isn't correct. I'm putting it in as a placeholder. Right, so the next thing is whatever I've loaded, I want to output as a character. So that assembly language... I've put loads of blank lines now. Well, that's going to drive me nuts. It's flashing now. Stupid thing. Right, I'm going to put OTC because that output the accumulator to the output window as a character. Then I'm going to stop. So I'm going to say on the next line, halt. But it was HLT. Notice they're all 3 letters. You don't always get that in real assembly language, but like I say, after half term, we'll look at some proper assembly language. Right, okay, and I want to store my number. So I'm going to say on the next line, dat, and you can pick your own, whatever's the most pleasing character for you. I'm going to go for character 69 because that's an E. Okay, so you pick your own favorite character from the alphabet, from the ASCII character set. We can actually print all the characters from the ASCII character set. Okay, so I'm 69 because it's E. Right, let's just, once you've done that, just click submit. Right, now, if we look at the translation, my data, where I put my dat in, my dat directive, that's at location 3. So now I know what memory location I'm reading my data from. So I'm going to go back, and instead of putting 1, I'm going to change that to a 3 and then reassemble it. Okay, so you can see in memory locations 0, 1, 2, and 3, we've got data, but all the data looks the same. It is just numbers. Okay, so unless we know what we're doing, if we was to look at the memory, when you're hacking, what you do is you work from memory and you have to translate back. You have to work out what's instructions, what's data. Okay, and try and, you can do this, you know. It's not impossible, but you have to become super nerd to do it. There's nothing wrong with being a super nerd. It's a cool thing. All right. Right, so we've got this. We want to run it though, don't we? To see what it actually does. There is a run button at the bottom. So if you run it, it goes really slow. And it'll show you the steps it's going through. Slowly. And it tells you, the little robot at the bottom in the bubble is saying what phase of the fetch execute. It's a simplified fetch execute cycle. It's using the arithmetic and logic unit to increment the PC. Eventually it'll get, oh, there you go. It's got to the instruction that output, and I've got my capital E. Then it carries on and it grabs the halt and then stops and it says, I've halted. Okay, so not a mega complicated one, but actually I've outputted something to the screen using this ridiculously simple program. But the process was quite traumatic in that I had to hand calculate the address of my data. There is literally no point in using an assembler if you're having to hand calculate addresses. We can get the assembler to do some work for us here. So let's go back to our program. Instead of manually putting in the address, what we can do is we can create something called a symbolic address. I do not like that cursor. Right, so I'm going to put letter. I must leave a space between a symbol and a mnemonic. Okay, so I'm going to put letter dat 69, and instead of 3, I'm going to put letter. When I submit that, it doesn't change the machine code at all. That's still translated into a 3. It goes, oh, letters at 3, at position 3 in memory. But it did the work for me. Now you might say, why have you bothered doing that? You're a bit of a loser. You just had a program that did it. You just made it more complicated. Now what I've done is I've done this. So if I was to put some more code in it, if I can type, I can't actually type HLT. I don't know, my brain didn't want to do it. If I put more of these in and submit that, the address of the data has changed. But I didn't have to alter my load instruction. The assembler did it for me. Okay, so symbolic addresses when we're programming in assembly language are ultra important. I will show you some proper ones, some proper programs We'll look at a program that I wrote for Pac-Man hardware. Okay. When we come back after half term, which I, for once, fully commented. Weirdly. Don't normally do that with me assembly language stuff. But I did because I wrote it for students. Okay, so we will look at that and you'll see some symbolic addresses. So effectively, this is identical to how a variable works in a high-level language. We give a name to a memory location. So you're literally seeing a variable. But we're doing this at low level. Okay. Oh, the aircon stopped. That's a relief. Doesn't feel like someone's revving up a fighter plane. Right. Anyone got any questions so far? Right. To speed up your programs, I think you can go on to the options and you can say default fast. So if you then run your program, bang, it runs really quick. It doesn't do all the slow train thing. Right, okay, I'm going to give you, I want you to work together, but I want you to have a go at a couple of programs. Now, I've not told you any more, okay? I want you to create a program. So let me go back to my whiteboard. Right, this program. So an LMC program, and it's going to do the following. Well, that's what I want it to do anyway. I want you to input a number. A number. It's not a number, it's a number. Input a number between 0, 1 and 26. And I want you to output the uppercase ASCII character for the alphabet. So 1 would be capital A, 26 would be Z, capital Z. And then I want you to output the lowercase. What was the relationship between lowercase and uppercase ASCII? What's the relationship? Anyone? No one remember from GCSE? Right. Let's write out a binary pattern, and I will write down capital C in lowercase and uppercase. And you can tell me what the relationship is. Right. So this one is capital C. This one is lowercase c. So that's big C and this little c. 32 is the difference. You toggle bit 5. Okay, you can't do that in Little Man Computer, but you can add 32 and you can subtract 32. Okay, so there is one more thing I've got to show you in Little Man Computer. So let me just show you this program. Oops, hang on a minute, I've got to get the right window. There it is. Right, so I'm just going to get rid of all that junk. If I want to add, so let's say I do low LDA number, number da 10. Right, if I want to add 1 to that number, how do you think I do it? I can't add 1. I can't say add 1. If I say add 1, it will load something from address 1 and add it. So to add 1, I've spelled number wrong. How the hell do you spell number wrong? I don't know. I have to do this. So I can say add 1. The quirks of assembly language. Well, I can't have constants. I can't, in most assembly languages, you can have a constant value. You can say add the number 1. You might put add #1 or something like that. But in Little Man Computer, we've only got variables. So whereas in a high level language, you would write something like this a lot. So let me just move that a sec. You might say A equals A plus 1. You can't do that in Little Man Computer. You'd have to say A equals A plus value 1. And you'd have to define value 1 equals 1 somewhere. This is the hardest thing about Little Man Computer. I don't know why we do it, to be honest. I'd rather we did full-on assembly language, which is what I'm going to do with you anyway, but working within the constraints of Little Man Computer is tricky. So yeah, so that's why I've written this program. So I'm going to run this now just to prove to you that it's going to load. So I've assembled it into memory, and there's the program there. You can see the 10 and the 1. I'm going to run it, and I think I'm in fast mode down here. So in the accumulator is 11, so it worked. Okay, so that's what you've got to bear in mind. So to add 32, you need to store the value 32 somewhere and give it a label, a symbol. Okay, have a go at that program. It's weird. Once you get over this weirdness of that everything's got to be stored in a variable somewhere and predefined, then you're all right. Okay, so that's your task. So have a go. Remember, I am recording this so you can go back through it. Right, okay, let me delete my junk. Anyone want to offer up their solution and I'll type it in? Speed it up. You can speed it up, remember, so it's not a major. You got to do OTC, remember. Anybody? No? Right, okay, so let's have a look at the task. We've got to break it down. So I'm stepping away from the little man and I'm just gonna look at it. So if I zoom out a bit, so I made that massive. Right, so I want to output a number based on something a user's inputted. Just standard task. So the first thing I need to work out is how do I do the input? Well, so to do this bit, I'm going to say, well, let's do imp. That'll get me an input. So let's get that bit working first. So I'm going to do this in massively little steps. So I'm going to go back to Little Man Computer. And I'm going to say, right, okay, then my first line's got to be imp. And if I submit that, yeah, okay, so I'm going to run that and see what it does. Right, again, everything's stopped by, if I look at the little speech bubble, it says input required. So I'm just going to put in 5 and press enter. When I press enter, it then proceeds. Okay, so fine, I got my 5, it's in the accumulator. Right, okay, so that was first job. So let's go back. Let's still think. Right. The uppercase character. So I know that I need to add. So if I've got the number 1, capital A, can anyone remember what the ASCII character for capital A is? Anyone bother looking it up? It's 65. I've got the world's worst memory, and I can remember the ASCII character set. All right? Right. So I want to transform 1 needs to turn into 65. What maths operation? Yeah. So I need to take whatever's in the accumulator and add 65. So I want I can't do this. I can't say add 60. I can't, well, I'm not going to do that because that's stupid. Add 64. I can't do that. Okay. It'd be lovely if I could, but I can't. So what I've got to do is I've got to store. I've got to say, right, I want caps, I'm going to call it, and I'm going to have a dat statement. So I'm going to say dat 64, and I'm going to say add caps. What I call it is up to me. So I'm going to try that. That's my fit. I'm going right. Okay, I think I've got that. I'm going to try that. Just see if the numbers work. So I'm going to go back to my little man computer, and I'm going to say, okay, next line in my program. I'm going to say add caps. Notice it tidies it up for me as well. Then I'm going to put the symbol caps, and I'm going to say dat 64. Right. So I'm going to submit that. It's assembled it for me. So I can see I've got an input, an add, and a dat. So I'm going to run it. It's waiting for me to put my number in, so I'm going to put my 5 in again, because I know that's 69, capital E. When I run it, and I'm running it super fast, I've got 69 in the accumulator, so it worked. Okay, so that looks good. I've just got to output it now, haven't I? So let me go back to my little scratch board. Okay, so I need to output it. So I need to make sure that this isn't in my way. So I'm just going to move that down. So I'm going to say OTC because that was the command. OTC, that'll output it. I need to put a halt in here really to stop it running into my data because that's what it tried to do. It went into my data. And I'll show you the consequence of that in a minute. So I will put a halt in eventually, but I'm just going to do OTC. So I'm going to add OTC to my code. And then hopefully that'll output. And this is just how we program. We don't try and create an entire solution in one go. We do it in bits and we test it as we go along. And it's really important in assembly language that you're doing it like this. Right, so I'm going to run that. 5, put my 5 in again. Well, hey, capital E. It worked. Not a very good proof. So I'm going to reset, run it again, and I'm going to put a different number. So I'm going to put 26, which I think is Z. Well, I hope it is anyway. Hey, got Z. It's not Z. You will get WG 6 points for that. I might send one in jest. Do you want one, Oliver? Right. Okay. So we've done the first bit. So let's go back. But I just want to explore this this problem where we've got an instruction followed by some data. I'm going to change that data and I'm going to put it to 100 and what should we have? Let's put 101. Change the caps bit to 101. I'm going to go back to default normal. I'm going to assemble that into memory. I'll submit it. Okay. Right, and I'm going to run it. So it's going to run slow. Okay, so it's going to get that first instruction, the input instruction. Hopefully the little robot's going to ask me to tap number in. So I'm going to go back to putting 5 in. Yep, does that. So 5 went into the accumulator. It's now doing the add. So it's getting address 103. So it's now going to get the data from from address 3. Adds that on. Okay, obviously that's not the right character, so it's going to output character 106, which is going to be a lowercase character of some description. Little j. Right, but now it's going on to get the next instruction, which was actually data. And that was an add instruction. So it's now going to add 103 to the accumulator. It's stupid, remember. The control unit is stupid. So now my accumulator's got 209 in it. So you have to be super careful. Sometimes when you're writing assembly language code, you want to make it really hard for someone to read. So you might actually organize data as instructions so that someone can't read it and you run into your data. But often it's a mistake you've made when you start executing data by accident. But the control unit is stupid in the CPU. It just assumes whatever it's fetching is a reasonable instruction. Right, so I'm going to put that back to 64. But that was a good demonstration of instructions as data. Right, so we've done the uppercase, so we just need to add another 32 to get the lowercase. So I'm going to add another dat to do the 32 add-in. And after my OTC, can you see how the assembler's letting me edit this? You know, I'm not having to like poke things into memory, which is how we used to code. Okay, you would write bytes of data to memory that was instructions. We used to get magazines, and you used to get magazines that had a little program that read a load of hex numbers and poked them into memory. And that's how you played games. So you spent all your time typing in these programs that went over like 10 pages of just hexadecimal numbers, which were all the data and code for a game. And then you hope you typed every single number incorrect so that when you ran it, the game loaded. but it's like it just wouldn't, and it's like, right, now I've got to go back through and check these thousands of hexadecimal numbers to make sure which one I didn't screw up. Ah, you don't know your born, you lot. You really don't. Right, okay, so I'm going to add on another 32. So after I've outputted, notice I don't have to reload anything. It's in the accumulator, the number. So I'm just going with it. So I'm going to add lower, and then I'm going to out it again. And then I'm going to halt so I don't run into my data. So I'm going to submit that. Okay, so got quite a substantial program. It doesn't do much, but it's actually taken up quite a few instructions now. It's occupying 8 units of memory. They're not bytes, but they're units. Okay, so I'm going to run that at decent speed. So I'll change my default to fast so it runs. So I'm going to do little. I'm going to do E again, so I get big E, little e. I'm going to reset, try it again, and I'm going to try another number. I don't even know where some of the... I'm going to do 12. Don't know what letter that is. Oh, L. Excellent. That's a nice number. I might reset and let's try another random. Let's try 17. I wonder what that is. Q. Interesting. Okay. This is the process. That's a linear program, though. Doesn't do anything interesting. It's just one instruction after another. So the program count is incrementing, and that's all it's doing. You can't really write many interesting programs without making decisions. So let's now have a go at another problem. So I'm going to do this one with you, and then I'm going to give you a different problem to do. Right, okay, so we are going to attempt, we're going to input a number. Oh, Teams just died. Why did that do that? It's just booted me out of my own meeting. I'm back. I know, I haven't joined it yet. Stupid. You what? I don't know. Well, it's a bit difficult when they're like having a ping pong chat about chuffing Rocket League. All right. What? What? No. For some unknown reason, Teams is acting like a stupid idiot. I don't know what it's doing. It's just booting me out of my own meeting. Right. If the number is less than 20, what we're going to do is we're going to output a character. So we're going to output the character Y. If you want to do lowercase y, that's up to you. I'm going to do uppercase Y, which is I know is 90. Else, we're going to output an N. I actually don't know what N is. Okay. Right, that's what we're going to attempt to do. So let's have a think. So we've got to input the number. So for this bit, we're going to do imp. That's the same. Okay. Now this bit, how do we check to see if a number is less than 20, do you think? We can't do compare. We can't do an if. Look at the instruction set. If I can find the right browser. Go on, Joe. I can't find that. Right. We can do a subtraction. Whenever we compare numbers on a computer, when you do is A greater than B, actually what the CPU is doing is subtracting. Okay, in the background. So we're gonna need to subtract. Now, what number are we going to subtract? Are we going to subtract 20 or are we going to subtract 19 or 21 or what? We want to know if it's less than 20. I can only test if we look at the instructions. I can't find my tab with the thing on because it booted me, I think. Well, let's test. So if we've got 20 and we do subtract 20, that's going to give us a result of 0. If it was 19 and we subtract 20, because we know that's less than 20, what would be the answer? -1. Negative. Now, on the little man computer, which I can't find my thing's gone and closed on me. Oh, it's there. There isn't anything that can check for a minus, is there? Okay, so there's one that checks for 0 or positive, right? So that's the 0. How? How though? Right. Let's try and formulate a bit of code then. So if we go back to little man, clear this program. Right, so we've got the input. We know we can do that bit. We want to try and do this subtraction. So let's do a sub 20, but we can't do 20. We've got to have a variable name, a symbol. So we're going to say 20. Yeah, right. What? So we input the number and then we subtract it from 20. Right, yeah. We can only subtract from a value that's in the accumulator. So if we're, no, but if we can do that if we store the number. So if we do store, we need to give it a name. I'm going to call it number. Store it in number. So we need to create space for a value called, oh, this is doing my head in. Number. Now, I don't know what's going in there, so I'm just going to put 0. 20 is going to be the value 20 stored. Right, so if we store the number that the user's entered, we then need to get the 20 in the, if we want to subtract the number from 20, like what you said, Ralph, I've got my input, I've stored it, that's still in the accumulator, and now I need to load the 20 into the accumulator. So I'm going to load 20, then I'm going to do the subtract like you said, of the number that we previously stored. So that's the first bit. I'm going to put a halt in here and just see what we get as a result. So I've got it in fast mode. I'm going to submit that, make sure it assembles properly. So I've got an input, then I store it directly. Okay, then I load up my value for 20. Then I subtract my number, and then we'll have a look to see what's in the accumulator. So we can do some testing now. Okay, so I'm going to run this. So I'm going to enter the value 18, which I know is less. When I look at the accumulator, it's got a 2 in it. So that's right, 20 minus 18 is 2. So that number is less than 20. What if I reset and run it with 20 this time? I get 0 in the accumulator. So that value isn't less than 20. What if I put 21 in? So I'm going to reset, run it again. My accumulator's now got minus 1 in it. Okay, so I've now got to make a decision on my branching. So I've got 3 branch instructions. One of them's no good to me at the minute, branch always. I've got to do it on a decision. So I can say if it's a plus, so 0 or positive. So is that the one we're going to go for? As a try, see if it works. Yeah? So I'm going to say here, so instead of halt, I'm going to say BRP. Now we need to give an address again. So we don't want to have to try and work it out ourselves. We need to have a symbolic address where there is an instruction. So we said we were going to output a Y if that was true. So I'm going to say true bit. I'm going to call it true bit, my symbol. I don't know where true bit's going to be yet. So I'm going to say true bit. And then what I want to do is I want to load up the value for Y, which I said was 90. So I'm going to have to store 90 somewhere. So I'm going to have Y 90 N. I'm going to just quickly look at what ASCII N is. I can't work it out in my head. So just find myself an ASCII table, the world's worst resolution ASCII table that was. What do you reckon it is? 78? And 77, you were close. It was close enough. Oh, yeah. All right, you were right. Was that genuine or did you look it up yourself? Wind up merchant. Right, so 78. Okay, so for the true part, I'm going to say LDA Y, and then I'm going to output it. So that's OTC, and then I'm going to halt. Now, what we've done is we've physically said, if we have got a positive value after that subtraction, change the program counter to here and execute this code. If that's not true, we don't have to do anything. We just carry on with the code underneath. So I'm going to just put a label, even though I don't need it. I'm just going to do it as a, same for me, false bit, I'm going to call it. And then I'm just going to say load N OTC and then halt. So I'm just going to assemble that so you can see that a bit better. Right, so this demonstrates a couple of things. Is that when we're doing branch instructions, we have change the program counter or just fall through and carry on. So you have to sort this logic out. But this is sort of how an if works, don't you? You have, if something's true, you fall through and carry on the next instruction. If it's not true, you jump to the else or to the instructions after the if. So we're just implementing that at a lower level. Let me put that in code. Let me try and copy that to Notepad so you can see it. I'll put it in Notepad++. That'd be better than that. Right, so that's the program as it is so far. I don't know whether it works. I might have screwed it up. But that gives me a structure to work with. You will find this mind-bendingly hard to start with because you've got to think in a completely different way to what you normally think. You've got to think infinitesimally small. So we're at all the numbers we want, all the storage we want. We've got to think about it beforehand. Notice that I'm putting all my data at the end of the program. Don't have to do that. Could put it at the start, but I will show you how that forces me to rearrange this in a sec. You'll notice we've got 2 stop points now as well. So depending on whether we do the false bit or the true bit, we stop. Right, get that in, try it, see if it works, follow it through. You should see that at least the program counter has to make a choice. Does it work? Does it? Have you tried it with different sets of numbers? Oh, is it? Oh, it doesn't matter. But does it work if it's less than it outputs one thing, and if it's anything else, it does the other one? Right. Anyone got any questions about that program? I don't like that, so there's nothing to stop you putting it on the next line down. It should actually work in Little Man. That. Hang on. Oops. Oh, come on. Yeah. That. Oh no. No. I thought there was something weird about Little Man. Supposedly, if you do that, right. See how it's done that? It's stopped assembling. It's got unknown instruction at line 5. It doesn't like it, even though if you look at the help file, it tells you about the formatting, and you supposedly can do that, but it doesn't work. So you've actually got to keep it all on one line, which means you've got to be careful with the width in characters of your symbols. So I might just call that false, and I might just call that true. And that at least gives me a chance of keeping it meaningful. When you're working at assembler level, meaningful is super important because you're not doing much. The instructions don't do much. So there's a greater need for explaining what you're doing. Okay, everyone happy that that works? I'll just Right, we have got our next lesson on Friday. Okay. Right, I'm not going to expect you to do this now. Right, I want you to do a two-step process for me. I'm going to give you a task to do, and I want you, don't think about how to specifically implement it in Little Man Computer, but I want you to try and break this task down so it's in really super simplistic steps. Okay, bearing in mind that the only instructions you've got are adding and subtracting. Okay, right. I want you lot. So I have a think about this, and obviously we'll carry this on Friday. Multiply two numbers. That's the task. So start off by thinking, right, okay, I can't multiply. How am I going to multiply two numbers together? First off, and then you can only do this multiplication. The only operations you've got are addition and subtraction. I don't know which are going to help you. They're the only two maths operations you can do. I could be mean and get you to do division, but that'd be a killer in this. Multiply two numbers. So that's your task for the rest of this the next 10 minutes is to start thinking about that. Okay? If you want to, before Friday's lesson, have a go. The nice thing about this is it's online. Okay? So you can get it. It doesn't work on a phone very well because of the way they're rendering it. It's old school stuff. Okay? But multiplying two numbers, that is your task. Yes. It just stopped. Because did it get what address is the PC on? What's at 10 in memory? Uh, let me come and have a look, man. Right, so multiplication using no more than addition and subtraction. It's not a trivial task. You can do it. Right, okay, for those that are not in the lesson, I'll end the meeting there. Teams has got such a bad interface. On the participation list, after it kicked me out and I came back on, it had my microphone as